This week we're going to talk about deterministic planning. And so last time what we did was look at this idea of deterministic actions and representing them in terms of strips. And this week we're going to talk about different ways of actually representing these essentially as search problems or as constraint satisfaction problems for which we know how to do the solution. So there are actually a number of ways of given a planning problem of actually converting it into either a search problem or a constraint satisfaction problem. So what we're going to do is look at deterministic planning. So given the description of the effects and the preconditions of the actions, for example, in the strips representation, we're given a description of the initial state, and we're given a goal to achieve, where a goal is a predicate on states. We're going to find a sequence of actions that's possible, so we can carry them out and result in the state satisfying the goal. The first model we're going to do is called forward planning. I'm going to search in the state space graph. So this is like the examples we've done before. So the nodes represent states, and there's an arc between S and state S and state S prime labeled with action A. If A is an action that can be carried out in state S, in terms of strips, it has the preconditions satisfied in S, and S prime is the state resulting from doing A in state S. So A is possible, and S is the resulting, and S prime is the resulting state. So plan is a path from the state representing the initial state to a state that satisfies the goal. So that's what we're going to try to do here. So here's an example of a state space in here. So so what we're going to do is we're going to assume that this is the initial state. We're in the coffee shop. The robot doesn't have coffee. The Sam wants coffee. There's mail waiting, and the robot doesn't have mail. Well, it turns out that in this story, there are three things the agent can do. It can pick up coffee, it can carry out PUC, it can move clockwise, and it can move counterclockwise. Okay, they're the three actions that it's possible for the robot to do. And the only things it can do, it can't pick up mail or deliver mail. It can't pick up mail because it's not in the mail room. It can't deliver mail because it's not holding the mail. Okay, so there's actions that it can't do. It can't deliver coffee because it doesn't have coffee. Okay, so in the pick up coffee one, according to the strips representation, what now happens is the only thing that's different is that now the robot has coffee. Before, the robot didn't have coffee, and now the robot does have coffee. It's the only difference. Once the robot has coffee, well, the only two actions you can do are move clockwise and move counterclockwise. Okay, and if you move counterclockwise from the coffee shop, we end up in the mail room. And if you move clockwise from the coffee shop, we end up in the office. Okay, and we can just get this from the strips representation. And then we could deliver coffee, and then you're in the office. The robot no longer has coffee. Sam doesn't want coffee now because Sam just got delivered coffee. There's still mail waiting, and the robot still doesn't have mail. Okay, instead of in this state, it could move clockwise or it could move counterclockwise. And of course, this state and this state are the same. So we can move back and forth between these states. And so the idea now is to form a sequence of these of doing this. This is called the state space graph, and it's going to be used in forward planning. Okay. So what we're going to do is we're going to construct the search graph on demand. We're only going to construct these so-called reachable states, the ones that actually can be reached from the start state. So a reachable state is one that can be reached from the start state. Okay. So if we want to do cycle check or multiple path pruning, we need to be able to find repeated states. And you might think that is sort of trivial, but it's not. It depends on how we're actually going to represent the states. And it's not obvious how to represent the states, but there are a number of ways of representing it. The first is a map from features into their values. So it's just like a Python dictionary, and that's what the code I'm going to do gives. Turns out that's often not a very good representation because it ends up being very big and usually only very small amounts of it change. Another representation is a path from the start state. So you could represent a state as a path from the start state. And if you want to query that state, we're just going to run through strips. Representation, say what's changed and what's not. So if you give path, if you're representing it as a path from the start state, we can compute what must be true in there. Okay, so what we're going to do is when we're doing this, we're going to improve our search efficiency. So we're going to use domain-specific knowledge. We have a heuristic function that estimates the cost of a complete state from the goal. So we'd like to estimate the cost of getting from a complete state to a goal. And that's what our heuristic function is going to try to do. Okay, and we're going to do in the assignment is to actually try and test out multiple heuristic functions. And then we got domains, so you could also imagine domain-specific pruning of neighbors. So maybe you could say, don't pick up coffee unless Sam wants coffee. There's a good heuristic that you might want to do. That you don't, if Sam doesn't want coffee, there's no point picking it up. We could imagine saying, unless the goal involves time constraint, don't do a no move action. So I didn't include the no move action. But you could imagine sometimes if you have to wait until 2 o'clock, it's just better just not to do any things. But if you don't no time constraints on things, or we want to, or there's no reason for waiting, then a no move action is never sensible. And you could have something, don't go to the coffee shop unless Sam wants coffee as part of the goal and Rob doesn't have coffee. Well, that might not be a very good heuristic, might not be a very good domain specific, because maybe you want to go through the coffee shop to get somewhere else. So sometimes you need to really consider what these are. But often what happens is that people build these planning problems, they try to define good heuristics, both in terms of heuristic function, but also in terms of ways to do domain specific pruning of neighbors. All right. So thank you.